So, we related time derivative of a vector in an inertial frame of reference and a frame which is rotating with respect to this inertial frame. So, what we had, some inertial frame of reference, origin, call it S naught, and then there is some other frame which rotates with respect to this with an angular velocity omega. And angular velocity we wrote as a vector, and the meaning is that this vector is along the axis of rotation of the frame, and then the direction on that axis, whether this way or that way, depends on how you are looking. So, if you are looking and you find that the frame is rotating anti-clockwise, then the omega is towards you, and you find that the frame is rotating clockwise, then omega vector is away from you. So, that is how we define this omega vector, very important. In fact, we will be using it extensively now onwards in this chapter and then in rotational dynamics also. So, this has to be understood. So, about this line, the frame is rotating, the other frame is rotating, which we are calling S, and this is the frame which we will be using. So, this is very important because we are using this particular frame which is S, and this S is rotating as seen from this inertial frame about this line with angular velocity omega. So, this is the situation. And then we said that if a vector is fixed in this frame, suppose I take a point here and say that okay, this is the vector, suppose this is the vector. So, wherever this x axis goes, as x axis of this S goes, this vector will go together with it. So, that means it is fixed in S frame of reference, or there is some other point you can take and say that okay, this is a vector, and not necessarily position vector alone, any vector which is fixed in this frame. So, that one can consider, and if you call this vector A, then we saw that in S naught frame, this whole frame is rotating. So, this vector A which is fixed in this S is also rotating, and that means as a function of time this vector is changing in S naught. It is not changing in S, it is fixed in S, but it is changing as a function of time in S naught, and therefore, we said that ddt of A, we have two things, one is in frame S, another thing is in frame S naught. dA dt is 0 in S frame, it does not change with time, it is fixed in S frame, and it is rotating about this omega as seen from S naught, it is rotating about this line, and therefore, S naught, this is not 0, and what this is, that we found that it is nothing but omega vector cross A vector. And if it is not 0 here, if this A vector is also changing in S, then the expression for this is this plus dA dt in S. So, if this is 0, this drops out and you just have this, and if it is not 0, then you have to take care of this also. This is because of the rotation of this frame, and this is because A vector is changing in that rotating frame also. So, when added together, it gives you the time derivative of A in that inertial frame of reference. So, this is what we had done, and now we will apply this equation for position vector of a particle. So, suppose this is now a point P, and here is a particle of mass m, and this may be moving in S frame of reference also, this rotating frame of reference also. So, this is a position vector, and to this position vector let us apply this. So, what do we get? dr dt as seen in the S frame, S naught frame, as seen in the S naught frame is equal to dA dt in S frame. So, dr dt in S frame, rotating frame, and plus omega cross r, omega cross r vector. This is what we get here. So, velocity of the particle in S naught is equal to velocity of the particle in S and plus omega cross r. So, now we will apply this equation on the velocity itself. That means, for this vector A, I will be using this thing, and that means this thing. So, what we will get? D dt of this V S naught in S naught frame is equal to. So, this is the whole quantity, this V S naught. I want its d dt in S naught frame in the inertial frame. So, what do we have to do? We have to write this term. This whole quantity which I want to differentiate, I have to differentiate in S frame. So, d dt of V s plus omega cross r in S frame, and then omega cross plus omega cross what? This whole vector. So, this vector V s plus omega cross r, this is equal to d dt of V s in S, this is 1, then d dt of omega cross r, and that is also in S, that is also in S, and then plus omega cross V s, and then plus omega cross r. Check. D dt of V s in S, this term we have written. Then d dt of omega cross r in S, so that term we have written. Then omega cross V s, that we have written, and omega cross r, that we have written. Now, what is this? What is this? This is acceleration of the particle as measured in S naught frame. We have first found the velocity of the particle in S naught frame, and then we differentiated that again in S naught frame. So, very consistently we are trying to write the acceleration of the particle in S naught frame, inertial frame. So, this is A naught. A naught is, what is A naught? A naught is acceleration of the particle in S naught. And what is S naught? S naught is our inertial frame of reference. And this is equal to, here this quantity is velocity of the particle as seen in the S frame, and then we are also differentiating that in S frame. So, this is the acceleration of the particle in S frame. So, in S frame I am finding what is the velocity, how it changes with time, and that is the acceleration. So, for this we will write A s. This is acceleration of the particle in S frame. Now, come here. We will take the angular velocity of the frame with respect to inertial frame as constant. We can also write the d dt of that also, if the axis also changes or the speed also, angular speed also changes. We can always write that d omega by dt, that is not a big deal, but let us practical cases, most of the time we deal with situations in which this rotating frame rotates about a fixed axis at a fixed angular speed. in that case this omega will be constant, and so we will say plus omega cross dr dt in S, dr dt in S. But what is dr dt in S? Dr dt in S is just V in S, in S frame. Okay, we are differentiating the position vector in S frame, and therefore, we get the velocity of the particle in S frame, this. And then I have this omega cross Vs here, and we have omega cross R here. All right, this and this are same. So, you can put a 2 here, multiplied by m everywhere, mass of the particle, 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 mass of the particle. Then what is this m and into A of S? Mass into acceleration. Okay. And now I will be dropping this S, because now it is very clear that we are writing acceleration, velocity, everything in S frame, in the rotating frame, and here this is in the inertial frame. So, this m A is equal to m into A naught, and A naught is acceleration of the particle in the inertial frame, and therefore, it is equal to the net force applied on the particle at that instant. Okay. In inertial frame of reference, I can use Newton's laws without any hesitation. Force, net force is equal to mass times acceleration. Here is mass times acceleration. So, this is the net force. This is total force, net force, real. All right. In inertial frame, there are no pseudo forces. In inertial frame, Newton's laws are valid. So, F is equal to ma, the net resultant force, all the forces acting together, take the resultant of that, is equal to mass into acceleration. So, this we write F net, and then minus, because what we are writing, this quantity. So, this minus everything. So, minus this quantity is m omega cross R, this is it, and then minus 2 times m, and then omega cross V, and all these quantities are in S frame. Okay. So, that is it. So, in S frame, mass times acceleration is not equal to the net force, as expected. As expected, S frame is rotating with respect to an inertial frame of reference. So, S frame itself is non-inertial, Newton's law will not apply there. So, mass into acceleration is not equal to F net. But then we say that okay, we will put from our side some terms which look like forces, and then we will say that mass time acceleration is this total force, this total force. So, these are the pseudo forces that we have to supply from our side if we want to use Newton's second law in the non-inertial frame, in this case rotating frame. Once you add this, then you are allowed to use all the techniques, all the processes, all the results of inertial frames of reference. Now, this quantity depends on the position of the particle. This quantity depends on the position of the particle, and this is known as centrifugal force. Now, we are defining centrifugal force in the most general way. Centrifugal force, this quantity is called centrifugal force, and this quantity is called coriolis force. So, the forces which are actually acting on the particle, they are all here, and these are terms which are added to that force to get this equation that okay, mass times acceleration is this quantity which we can call total force, and then use all that inertial frame type results. The important thing to note is the centrifugal force depends on the position of the particle, not on the motion of the particle. A very common misconception is, if a particle moves in a circle, then you have centrifugal force, m omega square r or mv square by r. Now, the centrifugal force has no reference to the velocity of the particle. Whether the particle moves, whether the particle is at rest, whether it moves in a straight line, whether it moves in a circle, whether it moves in an ellipse, whether it moves in a parabola, whatever the particle does, centrifugal force does not depend on that. Centrifugal force depends only on the position of the particle. Where the particle is, that will decide what is this centrifugal force. We will talk just now. But here the Coriolis force depends on the velocity of the particle. It is not depending on the position of the particle, it is depending on the velocity of the particle. So, this is the equation that we will be using. Our earth is a rotating frame of reference, we know, and so we will be using this equation for further discussion and examples and problems. So, keep this in your current memory. Mass times acceleration in the rotating frame is the real forces, then a centrifugal force, and then a Coriolis force. And centrifugal force is m omega cross r, and Coriolis force is minus 2 m omega cross v. This is also with a minus sign. Okay. So, let us talk little bit more on separately on centrifugal force first and then Coriolis force. So, let us say I have a frame which is rotating about this line with an angular velocity omega, and let us call it z axis. And there is some origin here, and you have a particle somewhere here at certain instant, you have a particle here, and that is the position vector r, okay, which can move in this frame. Your x, y, z axis are there, and it can always move. So, whatever x axis, y axis, z axis is already drawn. So, you have x axis, you have y axis, and this whole frame is rotating about this z axis. Let us take this example, or I can always choose my z axis along the axis of rotation, and then x and y axis will be in perpendicular plane, and this r may be moving in any way, we do not mind, we are talking of centrifugal force. It only depends on the position. So, at a certain instant the particle is here in my frame, and then this is the position vector, that is it, and we have to find what is this minus m omega cross r. This is the centrifugal force. So, let me use cylindrical coordinate system. Okay. What is that? In cylindrical coordinate system, the position of the particle is defined. So, if this is z, this is y, this is x, and here is the position. So, that position is defined in three quantities. You drop a perpendicular from the particle to the z axis, Why I have drawn this inclined type of perpendicular? Because the particle may not be in this plane of the board, z, y, z plane. It can be outside the board or other side of the board, and then we have to drop a perpendicular like this on the z axis. Now, this length is called s. So, your first coordinate is this s. What is the other coordinate? Other coordinate is phi. If you drop a perpendicular on this plane, and then from the x axis how much is the angle, that is called phi. So, if phi is more, that means it is more on the other side. Phi is 0, that means it is right here in this xz plane. So, that is how the, and then this is z. So, this phi is the second coordinate and z is the third coordinate. Okay. So, if you have an axis and then x axis, y axis, z axis, and particle is somewhere here. So, on the z axis you drop a perpendicular, and that length of the perpendicular from the particle on the z axis, that length is called s, and in that direction if you use a unit vector, that will be written as s cap. And phi means if here is the z axis, the particle is here or here or here or here or here or here or here. So, that we define using phi. Phi equal to 0 will be just above that x axis, and then phi changes means I am going this way, I am going this way, I am going this way. So, that direction. So, if I draw a circle, remember this particle is not going on the circle. If I draw a circle about this, then it will be, this is phi changing, 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 and so on. So, that direction is known as phi cap, unit vector in that direction is known as phi cap. Okay, and z is of course z cap, z is this. So, this is called z cap or k cap. This is how we define cylindrical polar coordinates or cylindrical coordinates, and let us use that here. So, if I draw a perpendicular on this, and this perpendicular length here is s, and this vector is s cap, phi vector will be going into the board, perpendicular to the board, going inside, and then we have okay, not going inside because I am taking this point not in the plane, but then you draw the circle and that, and of course, this z cap is in this direction. All right. So, what is this r vector? This r vector can be written as, this length which is z. You drop a perpendicular from the particle on the z axis, and that origin to that point will be z coordinate. So, this is z in z cap direction, this is equal to z in z cap direction and plus this s in s cap direction. So, this vector is this vector here plus this vector here. What is this vector? Z in z cap direction. What is this vector? S in s cap direction, and therefore, you have r vector as this. And what is omega vector? Omega vector is omega in z cap direction. So, what is this omega cross r? Omega cross r, this is equal to omega z cap cross z cap plus s cap. Now, z cap cross z cap is 0, and therefore, it is omega into s z cap cross s cap. And once again, just like I j k, you have the similar relation, you know, I cap cross j cap is equal to k cap and all that. Similarly, here s cap cross phi cap is equal to z cap and similar things. So, s phi z in that cyclic order, I want z cross s. So, z cap cross s cap will be phi cap, just like you have k cap cross I cap, this is j cap. You have I, j and k, s phi z, I, j, k. K cross I is j, z cap cross s cap will be phi cap. So, this will be phi cap. So, it is omega into s and this is phi cap. And then omega cross r, omega cross r. So, this is omega and then cross this omega s phi cap, and this omega is omega z cap. So, this will be omega square into s and into this z cap and cross phi cap. Once again, phi cap cross z cap will be s cap, and here I have z cap cross phi cap. So, opposite, phi cap cross z cap is s cap, therefore, z cap cross phi cap will be s cap minus s cap. So, this is minus omega square S and S cap. So, centrifugal force is minus m. So, this minus becomes plus m omega square S and S cap. So, what is the magnitude? Magnitude is m omega square S, and what is S? S is the perpendicular distance of the particle from the axis of rotation of the frame. Remember, axis of rotation of the frame, not axis of rotation of the particle. Particle is not going in circle, need not go in circle. Okay. So, this S is the perpendicular distance of the current position of the particle from the axis of rotation of the frame which you are using to describe the motion. And then S cap, what is that S cap? In that perpendicular, on that perpendicular you draw a line which is going away. So, that is the direction of centrifugal force. So, we will take from here, we will take some examples of centrifugal force, and then we will move on coriolis force, or the examples which are combining centrifugal and coriolis forces.